Okay, a theme we've encountered a couple of times in this chapter and also the past chapter is that if you do series expansions and you're clever in your choice of basis functions, that you can get away with using much fewer terms in your series expansion because your choice of basis function already incorporates lots of the physics of your problem. So if you're clever, you can save yourself some time, some calculation time. Here we're going to discuss a numerical method which is also based on that same principle, the principle of choosing your basis functions in a very clever way. The structures that can be studied by a method like this, which is called the eigenmode expansion method, more about why it's called eigenmode expansion in a minute, are typically layered structures. So for example, if you have a waveguide here, a narrow waveguide interface with a bigger waveguide, problems like this, if you come in with a mode here and you want to figure out what the reflected field is and what the transmitted field is. So layered structures are typically used for this method. Not just interfaces between two layers, but you can also have more like complicated structures. Like, does anybody of you know what a VCSEL is? You might have encountered this term in other courses. A VCSEL is like a vertical cavity surface emitting laser. So you have an active layer here which emits photons, and then there are Bragg mirrors on top and bottom, which reflect the lights. So you get a cavity like this. This is also a layered structure. And this is a structure which is amenable to this method of eigenmode expansion. So what do we do in eigenmode expansion? Well, the name basically says what the method is all about. We're going to expand the field in the eigenmodes of each layer. So this is the clever choice of basis functions. Rather than using sines of cosines to expand the field, we're going to write the field, for example, in this little section, as a weighted sum of all the eigenmodes. So, for example, I'm going to say it's 1 times the fundamental plus 3j times the first order mode, stuff like that. So a little bit more rigorously, we're going to write psi as a function, as a sum of an expansion coefficients of the eigenmodes. Of course, in reality, this needs to be done in a vectorial way. You can't do this in a scalar way if you want to get accurate results. But I'm just going to give a very brief overview of how the method works, such that you can understand its basic principles. So let's go back to our problem of an interface between two waveguides, and we want to study what happens in terms of reflection and transmission if you excite this interface. So the trick is that in the first medium, so let's call this medium 1, we're going to write our field here, for example, as the incident field, which could be the excitation with the fundamental guided mode, for example. And there's also the reflected fields. And the reflected fields we're going to expand as a sum of eigenmodes, of course, the eigenmodes in layer 1. And then these A's, they take the form basically of reflection coefficients. So you know how much field is reflected to the fundamental mode going back, to the first order mode going back, and stuff like that. For the field in the second medium, you're going to write that as a sum of eigenmodes, but this time as eigenmodes of the second layer, of course. It does not make any sense to expand the field in the second layer and the eigenmodes of the first layer. I mean, you could do that, but then you don't incorporate the physics of the problem, so that's not a good choice. And then these expansion coefficients B, they tell you everything about the transmission of the mode. So how much of the incident mode, for example, gets transmitted to the first order mode, to the fundamental modes of the second waveguide, stuff like that. How do you calculate these reflection and these transmission coefficients? Well, in essence, what you do is you impose the continuity of the fields. So you ask that, for example, the tangential electric field in medium 1 is equal to the tangential electric field in medium 2, and you do something similar for the magnetic field, the tangential components of the magnetic field. So of course that's another reason why you typically do this vectorial. Then you have these two equations here, which you can then use to calculate these reflection and transmission coefficients, because they will give you a system of linear equations. In the course notes, you will see what the result is of imposing these continuity conditions. You will see how we exactly derive this transmission and this reflection matrix. You can read that. It gives you an idea of how the method works. But I'm not going to ask stuff about this calculation at the exam. So the only thing I want you to know here is what the eigenmode expansion method is, why it's a good choice for certain methods like these layered structures, and the fact that you exploit the physics of the problem by writing the fields as a sum of eigenmodes, which is a logical basis set. So that's the eigenmode expansion method. Okay, so by now you have a good idea of many different optical methods. You have eigenmode expansion methods, you have brute force methods like FDTD, you have finite element methods, which are a little bit in between based on the variational principle. So what I also would like to do at the end of this chapter is give you another framework of thinking about solving problems numerically, and we will see that this is a very general framework, and many of the methods we've discussed earlier, we will see that they basically fit, sometimes partially, into this framework. So let's explain this framework, and it's a framework called the weighted residual method. And since it's a very general method, we'll also be studying a general problem. And the general problem is the following form: LU equal to V. So what is this? What do we mean by this? Well, our U, these are the unknown functions that we want to find, for example, the field in a waveguide. So U is the unknown of our problem. L, where does the L come from? The L stands for the linear, and it's a linear operator operating on our unknown function. So linear operators, of course, not only summation, but also stuff like integrals or taking the derivative. So these are all linear operations. So we have linear operators operating on an unknown function, and then there's a right-hand side, of course, which is the excitation. That's the known excitation, like a source, which is generating field components. So this is the general problem that we want to solve. LU is equal to V. If we apply this formalism to our friend the Helmholtz equation, so what is, for example, V in the Helmholtz equation? The right-hand side. The right-hand side is equal to 0, that we've discussed. So V is equal to 0. U is, of course, equal to our field function, which in the scalar case we called phi or psi, whatever. And what is the operator corresponding to the Helmholtz equation? So the Helmholtz equation is the Laplacian of psi plus k squared psi equal to 0. So our operator is equal to, this is a little bit more an abstract way of writing this down, but our operator, we can say that the operator of the Helmholtz equation is the Laplacian plus k squared. Because if this linear operator L operates on our unknown function u, what we get is this particular function. So this operator L, the way we write this down, basically reflects the fact that what this operator does if it encounters a function is it first takes the Laplacian of that function and then it adds k squared that function. So this is a little bit of a more abstract way of expressing this problem. Later on in chapter 4 we'll deal a lot with operators. This is something we get from the physicists. Okay, this is just a general framework of expressing what we basically want to solve. So how are we going to solve this problem? How are we going to find the U that satisfies our general problem? Well, the technique we're going to use is a technique we've used many times in the past. We're going to construct an approximate solution, U tilde, and that U tilde, we're going to construct that, should come as no surprise, as a sum of basis functions again. So we have these b sub i's, and again these basis functions, they're known. You have the freedom to choose them yourself, so preferably you do so in a clever way. So we have the known basis functions, and of course we have unknown expansion coefficients. So these are the unknowns, and the whole problem reduces from finding an unknown function to an unknown set of basis coefficients, expansion coefficients. So summation over I, and very crucially, of course, the summation ends at a finite number because we do not have sufficient memory to have infinite precision, infinite set of basis functions. So therefore it's an approximate solution because we terminate the series expansion, and hence we have U tilde. So our whole problem reduces to finding the best possible family of expansion coefficients U. So these U sub i's, we should choose them as well as possible. But what does that mean actually as well as possible? How should we choose U sub I? What's a very general principle that we can take as a guiding principle to come up with a strategy to find these U sub i's? What do you want in terms of relationship between your U tilde and your U, between your approximate solution and your true solution? Perhaps you're thinking that I'm asking a very difficult question, but I'm asking a really simple question. Who can give a simple answer to this question? You would like them to be equal. Of course, in practice, you will not be able to make them equal because you have only a finite number of basis functions. But in general, you would like the difference between U tilde and the correct solution, and I will call this U correct. The difference between U and U correct, you would like that difference to be as small as possible, right? That seems like a very sound principle to develop a numerical method. The approximation should be as close to the exact solution. Everybody agrees with that? Yeah, that's a fine thing to do. That's a good statement. That's a good thing to strive for. Is this a useful statement? I mean, can we use this statement to do anything with it in practice? Can we build a numerical method on this statement? Namely, that the difference between the approximation U tilde and the correct solution U correct should be as small as possible. Who thinks we can do something with this in practice? Who thinks in practice this is nice to have, but you can't do anything with it in practice? Have some people voting twice, so that's always an interesting tactic. Why did you change your mind?
Because you have to guess. You have to guess. You will not find a set of basis functions if you try to make the difference as small as possible.
So you want to make the difference as small as possible, right? So you need to have some sort of criterion to evaluate that difference. Otherwise, you're just shooting in the dark. But can you construct a criterion which evaluates that difference between U and U correct? Can you calculate the difference between the two of them? No, you can't. For the very simple reason, because the correct solution U correct is unknown, right? I mean, if U correct were known, then there's no reason to go through all the efforts. The problem is finding an unknown solution U correct. So U correct is unknown. That's exactly the stuff that we're trying to calculate. So how can you calculate the difference between an approximate solution and an unknown correct solution? You can't, basically, right? So one way would be just to give up and go home, but we're not going to do that. We're going to persevere and see if we can find a trick that will allow us to construct a numerical method. So some other approach. So what's something else we can do? Other approach that will still help us to construct a numerical method based on the principle that we should like to approximate the correct solution as well as possible. So if we look in the space where our solutions live, we have somewhere a correct solution, U correct, but we don't know where it is. Could be lying here or somewhere else. We don't know where it is. And we're constructing an approximate solution U tilde. But we have no way of evaluating the difference between them because we don't know where the correct solution U correct is lying. However, we still have something in our arsenal, which is our linear operator L. What would happen if we apply our linear operator L to what we have here? Then U correct gets transformed into L U correct, and U tilde gets transformed into L U tilde. what has happened now? We don't know what U correct is, but do we know what L operating upon U correct is? Yes, that's equal to V, right? L U correct is equal to V simply because U correct is a solution to our lovely equation here. L U is equal to V. So now we're in a different situation. We construct an approximate solution, and if we look at L operating upon that approximate solution, now we can calculate the difference between L U tilde and L U correct being equal to V. So now in this case, we have something which is known. Are there questions in the back? Is something not clear? Everything's clear? Great. Okay. So rather than looking at the difference between U tilde and U correct, we're going to look at the difference between L U tilde and L U correct. And the difference, of course, is L U tilde minus V. Now, a fancy word for difference or for something which is left over is called the residual. So we'll call this the residual. The bigger the residual is, the larger the error you make in solving your system, and hence that explains the first half of the title, weighted residuals. So here we have our residual. In this case, we don't really have any unknowns apart from, of course, our expansion coefficients U sub I. So we can calculate our residual R. We can calculate this completely as a function of our unknown coefficients that we're looking for, the U sub I's. If we write this in one dimension to make this a little bit more concrete, we have our residual, which is of course a function of x, right? And it's L operating upon our U tilde, which is a sum of a finite number of basis functions, unknown coefficients U sub I, known basis functions B of x, and we subtract the V of x. So this is our residual, and we can calculate this residual as a function of the unknown coefficients. And then hopefully by imposing some condition on our residual, we will be able to calculate our unknown expansion coefficients. So that's the next step. This residual, of course, should be made as small as possible, whatever that means, right? So what would be the ideal situation in terms of residual? What would be the perfect residual in a perfect world? Yeah, of course, ideally, you would like to have the situation that R of x is equal to 0, right? So identically equal to 0 for all possible values of x. Then you would have the correct solution, U correct. Will you be able to achieve this nirvana of a residual equal to 0 for all possible values of x? No, in practice that will not be possible because you restrict yourself to a finite sum here. If you had an infinite sum of basis functions in the limit, you would be able to approach that ideal solution. But that would be asking a bit too much, right? So asking that R of x is equal to 0 for all possible values of x if you have only n degrees of freedom. So what other approaches? So rather than asking that R of x is equal to 0 for all possible values of x, what are some conditions that you think would be good to impose on R of x that would help us to construct a good solution? Yes? Yeah, so if it does not work for all possible values of x, perhaps we can just live with asking that R of a certain family of points, R of x is equal to 0. And that seems like a good compromise, right? Other ideas, other things you could do? This is not the only possible strategy. You could have different types of strategies. Anybody has an idea or a suggestion? So asking R of x equal to 0 for all possible values of x, that's a bit too much. But you could also ask, for example, could you ask
But the error is so small as possible?
That the error, the energy in the system, like for example the integral of R of x or the integral of R of x squared, that you minimize this, that you minimize the energy in the error, that this is as small as possible. Or you could ask that the average, that this function R of x is on average equal to 0, that it's allowed to do something like this, for example. So these are all possible things you could ask, and depending on the condition you impose, you will get a slightly different type of numerical method. So these are good choices. This is something you could do. What I'm now going to propose is a different way of trying to make this error as small as possible, which seems very abstract, but later on we will be seeing that all of the stuff that you've been proposing is actually a special case of this very abstract, very general technique that I'm going to discuss now. So what is the approach we're going to take? So rather than asking this condition, we're going to do the following. We're going to look for, or we're going to choose another family of functions, a certain set of weighting functions. So these weighting functions, wj of x. So these are known. We will pick them ourselves, and depending on how clever we are in picking them, we get a good numerical method or a bad numerical method, or just a different flavor of numerical method. So we take a weighting function. This is a known weighting function, and we also need to define a scalar product. Remember, there are many ways we can define scalar products. So scalar products between two functions, like this. So we define it. Also, we have a degree of freedom in defining a scalar product that also there we can have a weighting function. So remember all the stuff we did with the Hermite polynomials. For the scalar product, we had a weighting function exponential minus x squared. The weighting function involved in the definition of the scalar product has nothing to do with the weighting functions wj of x you pick here. They're different. So you can have a weighting function for your scalar product, but you still need a family of weighting functions wj of x for the method here. So don't confuse these two types of weighting functions. They're both slightly different. But if we have a set of functions, and if we have the definition of scalar products, what can we do? We can impose that our residual r of x is orthogonal to each of these weighting functions for all possible weighting functions that we have. This seems very abstract, right? But later on, rest assured, I will show you that the stuff that you've proposed here are just special cases of what I'm writing down here, asking that our residual is orthogonal to these weighting functions. And now we have the full etymology of the name weighted residual method. We have a residual, and we impose that this is orthogonal to a set of weighting functions. So this orthogonality condition, if we write this down more explicitly with the definition of r of x, which we have up here, right? So this r of x is L, the summation of unknown functions minus v of x, and on the right hand side we have our wj, and we ask that this is equal to 0. So we can do this for all the weighting functions we have in our system. And of course, what we're going to do is if we have n basis functions, we're also going to pick n weighting functions. So if we repeat this for every weighting function in our set, we have an equation, we have n equations, and they have n unknowns, right? So this is something we can solve. And it's a linear system, because if you look at what's happening here, we can write this in the following way as a matrix L, which is related to the operators. A matrix L operating upon a vector U equal to a right-hand side equal to V. This is a linear system. And linear systems, we can solve them using numerical methods traditionally. Discussed this before. So for example, to give the relationship between the L's and the U's in this case and what we write down here, the U is a vector, is a column vector of all of the unknowns. So unknown 1, unknown 2, all the way up to unknown n. So it's a column vector. What are the vector V's here? If you just expand this component by component and write it down explicitly, you will see that V is actually formed by a vector where all of the elements consist of taking the scalar products of the function V with the first weighting function all the way up to taking the scalar product with the last weighting function. So this is another column vector. And then the matrix L we construct, you can see, and if you're not convinced, write down a couple of elements in this, write down a couple of equations in this system. You can see that the ijth element of this matrix L is given by L operating upon ith basis function and taking the scalar product with the jth weighting function. So everything here you can calculate. You know the basis functions, you know the weighting functions, you know what L looks like, so you can calculate your coefficient matrix. You can also calculate your right-hand side. You have your known excitation, you take the scalar product with all the weighting functions. So you can calculate then with standard linear algebra your unknown function. So this is how we go from a very generic problem, LU equal to V, with infinite degrees of freedom, and based on a choice of basis functions and a choice of weighting functions, we've transformed that into a linear algebra problem, which we can solve using standard techniques. So this is a very popular a very popular method, and this is why it has also many names, because many people discovered similar things individually. So it's either called the method of the weighted residuals, which is the name I've used so far. It's also called the method of moments. This is another way of calling this function, this method. And it's also sometimes called the generalized Galerkin method. And Galerkin was a Russian mathematician rather, and you have a biography of him at the back of this chapter. So I hope you understand the philosophy behind this method. Now the only thing that remains to be done is seeing how all of the choices that you proposed so cleverly to come up with good techniques to make this residual as small as possible, how the choices that you proposed are actually special cases of the generalized Galerkin method, or the method of moments, the weighted residual methods that we've proposed here. And of course, everything has to do with the choice of weighting functions, right? So let's look at some special cases, special choices of weighting functions. What are special cases? Well, the first thing you could do is take the following approach, that is, okay, I've spent lots of mental energy to come up with a good set of weighting of basis functions, right? I won't want to go through all of the trouble again of coming up with yet a different family of weighting functions. So I'm just going to pick my weighting functions identical to my basis functions. That's like a pragmatic approach, right? If you take this approach, then you get a method which is not called the generalized Galerkin method, but rather the plain, vanilla, normal, boring Galerkin method. So the Galerkin method, not in the generalized sense. And you can also prove, but we're not going to do that if you take an approach like this, that this is an approach which is equivalent with the variational methods. And you all know variational methods by now. They're very good in terms of not being sensitive to rounding errors. So this is good news if you don't take a special family of weighting functions, but just pick them identical to your basis functions. That's one possible choice. A different choice is saying, okay, my weighting function, wj of x, I'm going to pick this equal to a delta function which is centered at the point xj. Who has encountered delta functions or delta distributions in their past? Who has not encountered them? That should be the complement. It's not a complement. Nobody dares to admit that they have not encountered delta functions before, which is fine, of course. Everybody has a different background. So let me give you a very brief primer on delta functions or delta distributions. It's a complex thing. I could spend hours just talking about this. So I will just give you the engineering approach to delta functions so that you can understand what these things are. What is a delta function? A delta function, let's just say a delta function centered at the origin, so delta x, is a very special function which is 0. So delta x is equal to 0 if you're not in the origin. So that's quite boring. But the function makes up for this boring fact of being 0 everywhere, that the value at the origin itself, in a way, is infinity. So I'm taking a rather hand-waving approach here. If a true mathematician would enter the room here, I would be shot dead immediately. This is like the engineering approach to delta functions. So a delta function is a function which is 0 everywhere, except it's infinity at the origin. But it's infinity at the origin in a very special way, namely that if you try to take the integral of this object, of this delta function beast, that the value of this integral is equal to, somebody who has encountered delta functions before will know that this integral is equal to 1. Okay. So this is all rather mysterious and rather abstract. If you want something more concrete, you can take a look at the following family of functions. So let's start with a simple function, which is looking like this, for example. So the function is 1 everywhere, except for 0 outside of this block. And this has like a width of 1 and also a height of 1. So this is like a square. I didn't succeed in drawing it like a square, but just pretend it's a square. So this is a function, 0, 1, and then like 0 again. What I'm now going to do is I'm going to take this function and like squeeze it, such that rather than having a square like 1 by 1, I will have something which is 1.5 by 2. So what have I done here? I've made it narrower and higher. What about the integral of this function? What about the area under this curve? Well, since I've just made it twice as narrow and twice as high, the area under this curve, the integral, is also equal to 1, right? Now I can keep on repeating this procedure. I can keep on making this narrower and higher and higher. And if I keep on doing this until I'm blue in the face or until I reach infinity, what I will end up with is the delta function. So you see that you get something which is 0 everywhere, except at the origin, and there it's infinity. And since I've kept on halving and doubling such that I keep the same area under the curve, I will have something where the integral of this delta function is equal to 1. So this delta function is just a very special thing, which is the limit of this family of functions. If I now apply my weighted residual methods, I need to impose the fact that my residual is orthogonal to my weighting function. So typically our definition of scalar product involves an integral, and let's now put our weighting function of our scalar product equal to unity. For simplicity, the weighting function was a delta function, not a delta function at the origin, but at the point xj. And if I evaluate this using the rules of delta functions, you can prove, and I'm not going to do this, that just like the integral of this guy here, the integral of the delta function is equal to 1. An integral of a delta function with products with a different function, this will give you the r evaluated at xj, simply because it's 0 everywhere apart from xj. This delta function just picks out the value xj in R. If we now impose that our residual is orthogonal to this particular family of weighting functions, this is equivalent to asking that R of xj is equal to 0. And for this particular choice of weighting functions, we end up with what one of you proposed, namely, where do I have it? That I ask for the fact that my residual is not 0 everywhere, but rather it's 0 at a very well-chosen set of points, these xi's, and this is equivalent to choosing my weighting functions to be delta functions centered at these points. So this is also quite popular choice of weighting functions, which is why this has a certain name, this numerical method. This method is called the point matching method. For obvious reasons, because you match the solution to the true solution at a certain set of points. And if you translate point matching into something more Latin sounding, this is called the collocation method. Because you ask that two things are at the same location, are superimposed at a certain family of points. So you see, point matching or collocation is a special case of the generalized Galerkin method, the method of moments, or the weighted residual methods, all three different names for the same thing. What are other things you could do for your choice of weighting function? Well, you could ask that my weighting function is not equal to my basis function, but rather my linear operator operating upon my basis function. And you can prove, and this is something you will actually prove, you can prove that in this case, for this particular choice of weighting functions, that you will minimize the energy in your residual under the definition of scalar product that you have, that this thing is minimal. And this also seems like a good choice, right? You minimize the energy in your error. You try to make this as close to 0 as possible. And this is then called the least square residual. Now, for some reason, and I don't really know why that is the case, this method is not that much used in practice. Even though it gives you a very sound physical interpretation, you make the energy of your residual as small as possible. So like in the average sense, this tries to reduce the error. And what I want you to do now is prove this statement. And for that, you will make use of the fact that the definition of scalar product is something which commutes. So you will need that in your proof. So just to summarize what you need to do is you have here the definition of the method of weighted residuals, like this. And I want you to prove that there's an equivalence between doing this, the method of weighted residuals, and imposing the fact that the energy in the residual is minimal. So what you're going to do is you're going to start from writing down explicitly what the energy in the residual is. I want you to expand on this using the definition of R of x. Once you have that down, I want you to minimize this residual. How are you going to minimize the residual? What's the technique you're going to use for minimizing something? Remember Rayleigh staying at the Ritz Hotel? You're going to ask that the derivative of that expression, derivative with respect to all of your unknowns, you're going to impose that this is equal to 0. And then you're going to see, if you do everything right, that this is indeed something which corresponds to a weighted residual method with this choice of basis functions. So that's the task ahead of you, writing this explicitly and then taking the derivative with respect to all of the unknowns. Good luck. So let me help you on your way a little bit. So R of x, scalar R of x, we just follow the definition, right? So what is R of x? Well, we've seen a little bit higher on that this is the sum over I, u sub I, basis functions of I, minus v of x. So this is the definition of residual. And I'm going to take the scalar product with itself, of this function with itself, to have the energy in that function, in that residual. So I just copy and paste L I ui bi x minus vx. Right? Right? No one objects? Yeah. Again, it's always the same thing, right? So this scalar product is also a product, and we have a product of series expansions, and we've encountered this many times before in the past. If you have a product of series expansions and you take the same indices, you're bound to set yourself up for some horrible stuff later down the line. So make sure that you have a different summation index in that second factor. Okay, so hopefully that prevents you from running into your doom, and now you can continue solving this exercise. So let's take this one step further so that we're all on the same page again. So we have here in essence 2 terms times 2 terms, so 4 different terms. So we can write this as L, the sum over I ui bix, scalar product with L, sum over j uj bj of x. That's our first term. And then we have a second term. That's a term starting with the left hand side is L summation over I ui bi of x. But for right hand side we have minus v. So let's put the minus here. And then we have v of x. So this is number 2. What about number 3? Number 3, yeah, that's not. Number 3 is the product of these two guys. So this thing with this thing. So that's V times a sum. Now remember I told you that the scalar product is commutative. So that's actually the same as the scalar product of this sum with V. Now here it's a sum of j's with V, here it's a sum of u's with V. However, in this case that doesn't matter because we don't take the product of two series expansions. This is just a single series expansion. If you don't trust me, just write it down explicitly in all the different terms. But this is exactly the same term as the one we had before, so we can put -2 here. And then the final term that we have is just simply the scalar product of V with V. So this is the residual a little bit worked out. Yes?
Are all functions real?
Are all functions?
Real.
Yes, yes, you can, in this case, you can take advantage of the fact that they're real. Of course, you can do clever tricks with also complex-based functions, even complex spatial coordinates, if you want to get fancy. But for this thing, you can make use of the fact that it's just a real valued function. So the next step is taking that expression and deriving it partially with respect to a certain unknown UK, so an arbitrary but fixed value of these unknowns. And then you need to take the derivative of this scalar product. Now, of course, for those of you who are really not sure about what the derivative of the scalar product is, just go back to the definition. It's an integral of the product of these two functions. If you take the derivative of that and you assume that you can exchange the order of integration and differentiation, then this is just plain and simple the integral of f prime g prime f dx. And so if you evaluate this, you will see that just the same rules apply for taking the derivative of scalar products in this case as composed to regular products. So using this knowledge, you can now proceed and take the derivative of that expression above. So let's take the derivative of this thing first. And let's start with taking the derivative of the first factor. So we pick a certain UK and we take the derivative with respect to UK. So of course we don't need to worry about p being a function of x. We're not taking the derivative with respect to x. We're taking the derivative with respect to a certain value UK. So what is the only thing that's left here? The only term where you find the UK is the term where I is equal to k, right? And you just find then L UK BK, and taking the derivative with respect to UK is like taking the derivative of x with respect to x, that's just 1. So the only thing that's left over in this case is LBK, right? If this is a bit confusing to you, just write this down explicitly as opposed to a summation. Just write down a couple of terms and you will see what we mean here. So we just follow this recipe here. We took the derivative of the first factor. Now let's copy the second factor. That's L summation over j uj bj of x. And then we need to take the sum of just having f. So we copy f. That's L the summation over I ui bi of x. And then we take the derivative of the second factor. Taking the derivative of the second factor is the derivative of this thing here. The only term where we have a UK present is if j is equal to k, and then the derivative is simply LBK. So this is taking the derivative of the first term. Let's have a look at the second term. That's already a lot easier. So here we simply get -2. Of this series expansion, the only thing that we end up with is a term where I is equal to k, LBK V of x. That's the derivative of our expression. That's the derivative of the energy in the residual. And if you want to minimize this, we want to make sure that this derivative is equal to 0. So this is the condition that we impose, and we impose this for all possible values UK. We can simplify this a bit further. If you look at these first two terms, you will see that if you apply the fact that our scalar product is commutative, So you can just swap the order around. And if you now realize that whether there's an I here or a J, in this case, because we don't have a product anymore, that doesn't matter, you will realize that these two terms, they're actually exactly the same. So you can simplify this and then divide everything by 2. So if you just focus, for example, on this guy, you can write L summation over I, Ui, Bi of X, LBK, minus, and then if we also make use of the fact that this is commutative, we can change this around in order. We have V of X, LBK of X should be equal to 0. Now, if we just combine everything, Ui Bi of X minus V of X LBK of X is equal to 0. What this actually means is that our residual, because this thing is nothing more, nothing less than our residual, is orthogonal to LBK. And this is precisely the method of weighted residuals, right? We started out by minimizing the energy in the residual. If we do that, we end up with a condition like this, and this is precisely the method of weighted residuals, where for the choice of weighting functions, we choose L times the basis function. So here we prove that these two things are equivalent. So again, this was just another nice exercise, playing around with series expansions. You know I like this type of stuff. And it gives you the proof that these two things are equivalent. Okay, so just to wrap up this chapter, we've seen the method of weighted residuals. We've seen that special cases of this method are, for example, the point matching methods, minimizing the energy in your system, stuff like that. And let's now also make the link to the techniques that we've discussed in the beginning of this chapter and see how they are related to this method of weighted residuals. I'm not saying that these are methods that fall exactly under this family of weighted residual methods. I'm just saying that there are some concepts which you can find which are common between different techniques. So for example, if you look at the finite element methods that we've discussed, how are they related to the method of weighted residuals? Well, of course, one thing they have in common is this choice of basis functions. They're all working with a set of basis functions. Something I can say here, a little bit of extra terminology, is that in this case the basis functions, they're only valid in each element, so you don't have basis functions which span the entire computational domain like you have in eigenmode expansion. So these are called subdomain basis functions because they're only valid in parts of the domain. In the method of finite elements, we have not talked about weighting functions. So this is indeed an example of a technique where for weighting functions and basis functions, we choose the same family of functions. And we've also seen that this is indeed a variational method. So again, I'm not saying that the finite element method fits exactly under this framework of weighted residual methods. I'm just saying that there are concepts which are common between them. For the eigenmode methods, eigenmode expansion methods, also here there are some parallels. You will see if you follow the derivation in the course notes when we try to derive the transmission and reflection matrix, that there's also some sort of multiplication with the weighting function going on to derive that. But you will see that in this case the weighting functions are also equal to the basis functions. By the way, sometimes people also call these weighting functions the test functions, but that's the same terminology applied to the same concept. And in this case, both the basis functions and the weighting functions, they're the eigenmodes in the waveguide. So this is what is common between them. And you will also see, if you follow the derivation, that there's a definition of scalar product, which involves the electrical and the magnetic fields. And the definition that's being chosen there is the following: vectorial product of E with H. By the way, some physicists might get upset by this definition of scalar product. By the way, it's a definition, so you have many degrees of freedom. There are some people who prefer a definition with a star here, for the simple reason, because why do you think physicists would prefer a definition of scalar product like this? What's the physical meaning behind this quantity? Yeah, it's the pointing vector, right? That gives you the interpretation of energy in your system. So physicists are so hung up about physical interpretation that they really want a star here, but you can just as well have a definition where there's no star here, just as long as you're consistent within your method. And in this case, in this method, it's actually more advantageous not to put a star there. I remember a long time ago when I did my own PhD defense, I did that on eigenmode expansion, and there was a physicist in the audience, and there was engineers in the audience, and the physicist really insisted that I should use this definition of scalar products. And of course, the engineer was perfectly happy with not having a star there. So what happened during this defense is that the physicist and the engineer basically discussed among themselves for the whole defense, and I was just sitting there watching them fight. Okay, it's not exactly true, but this is indeed something that happened. So just to illustrate the point here is that you have a degree of freedom in choosing a definition of scalar product. You only need to be consistent, right? And then finally, we had our finite difference methods. If you really want to shoehorn finite difference methods into this framework of weighted residuals, you could say that, okay, I'm also expanding this in basis functions, but the basis functions I'm using for the finite difference methods. What basis functions are you using here? Guys, we've seen a couple of minutes ago, the basis functions are the delta functions, right? Because you only pick out the fields at certain discrete grid points. Okay, that brings me to the end of this chapter on numerical methods. Next time we'll tackle chapter 4, which is all about symmetry, periodicity, and how that impacts the solutions of the Helmholtz equation. So see you next time.